Hi everyone, welcome back. Thought I'd give an update. So I've done quite a lot. Not sure where to start. So I decided to convert to Go for now. Basically just so we can implement lots of things, get it working, test things, implement the nodes, and then see it working, because converting to LLVM takes a lot of effort, and you need to have a lot of things working already for it to actually work. So it's easier just to kind of convert to a simpler language and then convert to a more complicated language later when everything works. So that's what we're doing. Then I've had lots of other things. So I had here compiler settings, which literally just has the stuff if you want to add stuff or not. So we have a language target, which is either for now is either Go or LLVM. We could add more later if we wanted to. That would just take a bit more work. Back to here. So basically I just set this at the start. We create compiler settings and then we set them. And separate expressions basically means, let's say you have, it's basically like what I did before. So if you have, for example, int value equals, say a plus b without capitals, a plus b plus c, like this. If you separate the expressions, it will convert that into int, I don't know, temp1, int temp1 equals a plus b, int temp2 equals temp1 plus c, and then go int value equals temp2. That's basically what it would, how it would work, and then make that into LLVM or whatever. So we have this separate expressions, which for non-LLVM languages, in LLVM you literally need to do this, but in saying Go, if you want to, have it just regular like this, not separate the expressions, then we set this to false, and we can set it to true, and then we can compare it and test things. Basically, see is it converting the expressions correctly or not. Show input code. This is just a load of settings. Just show debugging stuff, show addition, show definitions, show AST nodes, just for debugging basically. That's what I got these for. It does mean that when I'm actually converting the code, I have to check if we're separating the expressions each time, and then do a different one each time. Another thing I did, I'll just load up an error quickly. Say error 1. Alright, so run this. So it should give me an error. We're expecting an error. Yeah, okay. So what I did was there was a problem with how we were counting the characters in the parsing code. So I basically fixed that, which I'll show you in a minute, and then added this thing. So basically it will put exactly where the character is, hopefully. And the way I tested that was, get this off, and I accidentally pressed page down, which I always seem to goddamn do. I meant to press home, but press page down. Run tests, and I'll show you. The reason why I don't use inbuilt tests is you have to add them to the build system. I'm too lazy to do that. When you have an actual project, you have to actually add them into the build. I can't be bothered. I'd rather just comment out a function. Like, it's just like, it takes me literally like 2 seconds to do that. But if you see here, we're testing it. Basically, we're just going through each character and then putting this wherever it is, and it works. So that's basically me testing it, showing it working, because that's what we use to show error messages. So now we know exactly where the error message happened, because before, say if it was something like a for loop, which I'm not sure if I have one. I do have one. So say if we have a for loop, we have I multiple times in this line, but say if we miss something, like say going to 4, and let's change this to be, let's take away the semicolon, and we should get an error. Yeah, we're missing we'll show exactly where, because which I, it's better to actually show you which I, so that's a lot better now. Put the semicolon back. Alright, so yeah, you can see it kind of converting into Go when it actually works. So when I do this, so here are the AST nodes or whatever. So I've done a lot of stuff. I've done quite a lot of stuff. I'll show you I made a checklist, which I can show you what we're doing. So they've got compiler features, the parser, AST, checking. Checking is probably the hardest thing to do, because if you want to check if your code is correct, so you have to check variable names, you have to check definitions, you have to check redefinitions, You have to check scope. You have to track the scope. Does it exist in this scope, or is it gone out of scope? You have to check values. Are the values compatible? So if you say integer value equals string value, what does that even like? You can't say like this. So int value equals hello. Obviously that's not compatible. You got to check it. Or it could be like things like integer overflows if you want to check for that or not. Some people, don't bother. It could be also that you call a function. So like, I don't know, function 1, but the function returns a string. This obviously gives you an error. If you have like returning a string, this is a problem. So you have to check, you have to look at the definition. This is just a big problem and really difficult. Just if you have no checking at all, it's a lot easier. But yeah, difficult to convert to LLVM if you don't do that. And here's my Go implementation. So basic vars, I haven't done chars yet. That's like really not much work at all. Just haven't implemented it yet. Arrays, lists. I'm not sure how to implement lists. I'm not sure exactly. Enums and structure are actually annoying, but they're not too annoying. But they're more, it's like a day of work at least. Globals I just haven't done yet. Printing's fine. If else doesn't work, I just got to do that. I think continue actually works. I haven't tested it though. I could test that now, but not really the video for that. But most things work. I'll show you, for example, here we're literally just going a for loop and then create the for loop in Go and then printing the I, and that's all we're doing. So that works. You can put multiple things in the print as well. So print line converts to fmt.println. Anyway, I'll show you. I'm not sure exactly where to start. So there's a few things. So first I'll show you the parse code. So in the parse code we have, so before, I think I was literally, if we go over to should skip, it basically had a plus equals here, plus equals 1 in the skip, which obviously you shouldn't do because you don't want to skip on every character. You don't want to add 1 every character. So what I did to fix that was basically, not here, process character. Say for that read string, for example. Yeah. Oh, we have character index here. So for every character we find, we plus equals the index. And then we plus equals the index here. And then the same for everything else. So we're basically just plussing the index every time we find a character. And here we do the token text.length because it could be, plus equals, it could be plus. And that's basically how I fixed it, and for now it works. And that's basically it. For everything we're adding plus equals length. That's it. Alright, so over to the Go code. So here I put a kind of a step in between. So when we go to convert code, also we did also get a few definitions, but it's minimal really. We basically get the definitions of functions. I'll show you this. I'll show you this quickly. If we put to show definitions to true and spell it correctly, then I'll show you. I don't think we have many. Yeah, we have no global and we have void main. So it just shows the functions. If I go to maybe add, it will show it better. Say add. I don't even know what add does. What does add do? That's what we want. So add here, yeah, it shows basically I32 add, I32A, I32B, void main. Pretty simple. And we can use that to check, the return type and the function types and the those types. But we are actually just using the AST at the moment because that's the simplest thing to do, and then we can kind of rebuild it. I might make a more complicated or a different structure, but for now I'm just using ASTs just because it's kind of built for it anyway. So I'll show you how we do that quickly. So in analyze code, static analysis, we just have analyze code. We have global variables map. So we're using a string hash map, which basically just means it's like a hash set. It's like it could only have a unique value because that's what we want. And I believe we use errors if, yeah, so we put it in global definitions and we have a lot of error checking. So we have function is defined, and that will be a bool, append function. So, and we have a semantic error, which basically just means function redefinition or variable redefinition or out of memory. That's literally the only thing we have, because it could be a redefinition, and it has this function get or put, which basically sees if it exists, and if it doesn't exist, it puts it inside the hash set. If it does exist, it gives you it. So we're basically just saying, does it exist? If it's found existing, then redefinition error, and that's basically it for hash sets. I don't really know too much about them. This is kind of the first time I'm actually using them in Zig. Where are we? Okay, back to this. So we create this. Then I don't remember what we're doing here. We loop through all the nodes. Then we look for function declarations. And then we basically just get the stuff from the function declaration. And then if it's a declaration, a var declaration in the global space only, we're only doing globals. The problem with doing local variables is it's based on scope. That's annoying, because if you make a for loop, the I will exist only for the for loop, then you have to delete it. You can't use it after that. And we're putting the code in here just because we could have an error later, so we might want to show the code. But for now, we don't actually have any errors that could happen. But we'll do that later when we actually properly do analysis, because that's probably the hardest part of this project entirely, is making sure things actually work. Because in theory you could depend, I mean LLVM doesn't have that bad error messages, but you probably want to have your own. It's just better, but it's a lot of work. Basically that's all I'm doing. I'm just adding the AST data, and then I print that, go into main, print all data, global definitions. So print function declarations. Go to this, and then we go print node details, a load of chain of calls, which basically it just recursively print parameters, print node recursive. We print the node, and it will kind of, how would you say it? Just look at the function, it'll be easier. So we just print the text. That's it. We print the text. I'm trying to remember what this is. The type node? The type node, right, okay. And we make it blue. So we make it blue, so we're printing the type. So if I show you here, we make the type blue, and then we reset it. And the type could be, because it could be, for example, it could be this pointer to int. Or it could be this pointer. Or it could be this into, So it could recursively go down. We're probably not ever going to do multi-dimensional arrays because it's terrible. It's so complicated. It's a nightmare. Like, just trust me, it is really difficult. I think what Zig does, actually, is it kind of pretends. It pretends to do multi-dimensional arrays. It has one array and then just uses like a separate index. Because technically you don't actually need multi-dimensional arrays. Say, for example, you create like kind of a tangent. Anyway, we're probably not going to do it because it's complicated. But because it's like complicated, it could be complicated. We check if it's null and just recursively call this until we printed them all, and that's it. So we print the type, then we print reset, then we print the name, and then we print the parameters, which does almost exactly the same thing. We just go through the type and then go through the name, type, name, and that's it, and that's what we get from here, which shows that you can use ASTs for actually checking stuff. It's just a bit more complicated. Anyway, so that's all we got for that. Then we go to convert code, and we have one step in between convert code because we want to know what we're converting. Are we convert it to LLVM or we convert it to Go? And they're different. So we convert to Go, and then we have quite a lot of things implemented in Go. We have Go array, Go assignment, Go body, Go convert, Go declarations, Go flatten, Go for, Go function, Go if, Go print expressions, Go print, Go return, Go utils. And it's kind of quite obvious what I'm doing here. I mean, the ASTs are exactly the same. We're simply just making it work. So for example, at the start of Go, we just put in package main import FMT because we're probably going to use that. So one problem with Go, that's really annoying actually, because I don't really like it. It just annoys me. Is it will give you an error if you don't have a used variable. So if you have an import like FMT and you don't print anything, it will give you an error, which means you gotta do like this. You gotta put that there, just to be annoying. The problem is I don't really want to have that in my language, and it's also really annoying to have to check that, because it means I have to track every variable and then track if every variable has been used and then give a warning, and then just like it's just like really annoying. But what you can do, say if you make an integer, and we can make an integer in Go like this, var value int equals 10. I don't like inferred types. Then you can go you could do this and it will automatically use it, but then you can still use the value afterwards. So you basically just, if you want to be lazy, just write this after every variable declaration and then just forget about it. But I'm not sure how to do that with imports. If you can, there's probably a way, but I haven't got to it yet, and I'm not even at the point where I can automatically convert it, so it doesn't really matter. Anyway, so I'll just show you a few of these things. We have Go array, which is kind of minimal at the moment, because I don't remember how arrays work. But yeah, we basically we have this thing print expression, which is for when we don't want to flatten the expression, because again, either we want to like say a plus b plus c and just print it, or we want a and then in separate variables. But I have print expressions basically is exactly the same as flatten expression, but it just prints it in order. That's all you need to do, and it depends on the node what we do with it. So here we have the array group of how it is. The way I have array groups is because it could be multi-dimensional, it could not be. And these are all children of that, and that's how arrays work. But basically, I mean, I kind of infer the types, which I don't like doing, but it's just a lot less annoying than, because you have to know the length, and I could use the length. Anyway, I'm going into a tangent. I just did that just for simplicity at the moment. I might later, you know, actually put the type here, put the number in. Go assignment. This is pretty simple. We basically just print expression and then just print it. That's all. It's pretty simple. Go body has all the types. We have a load of stuff that, you know, I've skipped over because I haven't implemented that yet. I was actually trying to do switch statements before this, but switch statements are deceptively complicated. They're really complicated, actually. It's easier just to do else if, actually to implement it. Go convert is this the base thing. Go declaration. So yeah, we use var the type, and we get go type. We convert to go type, which just converts it like this. Yeah, void just, you know, converts to nothing. Where are we? Go declaration. It's pretty simple, really. It's not that complicated. We get the data from the AST and then put it into valid Go code. I have this thing add new line with tabs, which things like, why do I have this? Basically, you could have a declaration or a reassignment or something like this inside a for loop. So you don't want to check, you don't want to add a new line within a for loop. So you want to add the semicolon, no new line. That's basically why I have that. Because sometimes you don't want to add a tab or new lines, you just want to keep going inside a for loop. That's the main reason for that. We go flatten, which is just flatten expression, really. It's just flatten expression. Which I don't have everything here yet. I've got a few things I haven't actually implemented yet. Well, flatten we're not really using mostly. We're using the print expression, which just prints the expressions in order, basically. You have array access, you have all these things. All these things are kind of done. I should really put this into a separate function, but I couldn't be bothered. I'll do it later. You know, go print. I mean, go print is very simple. It's either new line or it's not. So we flatten the expression of the whatever it is inside a for loop. So we go through each child and then print or flatten the expression, depending on if we're separating expressions or not. Then for each one, we just print it, basically. And then if it's new line, we put print new line. If it's not new line, we put print. Pretty simple, really. Then say return. I mean, return is pretty simple as well. Process return with flatten. So we've got two things just in case there's a flatten or not. But yeah, that's basically it. I mean, if statements. You know, we put while inside if statements because whiles and if statements are exactly the same thing. Maybe you don't know the. So I'll quickly load this. Let's say if 1. I don't even know what's in if 1. If 1, something like this. let's go if2. If3 is go if3. If3 is a bit more complicated, so you can see a lot more of the ASTs. All right. So basically, we have this code. We add. We get the add result. We see if bool is true. We just set it to true because it is true. Then we say if add result higher than 10 and is true equals true. Then we print line. And then we convert that into Go, which is almost identical code. It's just like the things are inverted mostly. I do have int as an option, and it just converts to int in Go just for simplicity. But if I show you the ASTs for this, you have function declaration, the return type is on the left, parameters on the middle, and the children is A, int, B, int. We have the function body, which is on the right, which is a return expression, plus A plus B. We have the function declaration, main, return type, void, parameters none. The function body, which is right, and then we have declaration add result, which is a child of the type function call, add 10 plus 10. Then we have declaration is true, we set it to true, bool literal, if statements. So I think in if statements, so the left is the bool expression. So we have to kind of nest them because we have and add result higher than 10, and the identifier is true. And then we just have the if body, which is on the right. So it's just left, right, simple. With for loops, it's a bit more complicated because, say for, so for loops, it converts this, prints it, and then into this, which is almost exactly the same. You just take away that, you take away the actual, clear explicit declaration because you can't do that in Go. Anyway, yeah, it converts to this. So the for loop, we have it's a child with a for condition, which is whatever's in the brackets, which is separated into 3 separate nodes. We have the basically we're presuming that it's a declaration, a bool expression, and then an assignment. Anything else will probably give you an error because it's just simpler, because you have no idea how complicated an if statement can be. You could put nothing. You could put 10 declarations inside the first part. You could put nothing inside the middle part. You could put anything inside the middle part. You could it's a nightmare. And then the last part, you could put nothing. You could put minus. You could put plus. You could put like a declaration. Like it's just like there's almost anything you put inside a for loop. They are very complicated. For now, I just basically presume declaration, bool expression, assignment. Like the standard, create a variable, see if it's less than that. If not, do something. +1, -1, whatever. So we're just presuming it's that. And if you want to make it more complicated, then use a while loop. That's what they're there for. Anyway, that's basically how it works. And then so it's the left is the condition and the right is the body. And the body works exactly the same way as a function. You get the body so you have the function has a body, and then the for loop has a body inside the body of the function. They're nested, as you can see here. So we have the function body, and then inside the function body we have the for loop, and inside the for loop we have the for body. Hope that makes sense. I also added a few more things to the parse. So for example, some things didn't work, like colon wasn't added. Added colon. But stuff like this. The code is in the description if you want to copy it yourself. Anything else I'm forgetting? Not sure. So yeah, for now on, I'm just going to get the Go part working. Right now, it doesn't actually create because what you could do is create a file, and then you have to create a go.mod, and you have to create a folder for it. Then you'd have to run the command go build dot to get it to run, or you could just save yourself a load of effort, copy and paste it, create a Go project, and just copy and paste it into that, like I can show you. I have this project just for testing stuff. I just copy and paste it, do this, run that again, and that works. 0 all the way to 10. Is that correct? Yeah, I went to 10. Okay. Anyway, so instead of going through the effort of creating a folder, creating a go.mod, creating a Go file, running the command, I just copy and paste it and then test it that way. Because then I don't have to. Simplicity is just a lot easier. Of course, the goal later would be to actually make a file, make a folder, print it, run it. But for now, we're just going to do this. Because, you know, I want to actually finish this project at some point. I don't know if we'll actually do that, but yeah, so here I'll go back over the checklist. So chart is very easy to do, float is very easy to do. Finding the compatibility and the casting's a nightmare. Lists are pretty easy to implement in Go. I'm not sure how to do it in because I mean the problem is the syntax. So I mean, say in Go, for example, if you do whatever, like say I don't know, slice thing, I don't care what you want to call it, is this, that will actually be a slice, not an array. And if you do this, like with 5, that's an array. That's how it works in Go. I don't really want to do that because this should be like an inferred array. That should be an inferred array. So I was thinking of doing something like maybe list, and then int. Something like maybe something like this. I don't know. I don't know what to do. It just I'll often like you plan syntax. You plan, oh, I want my syntax to be like this. And then you try to implement it and find, oh, it's actually impossible to do this, or really hard. So you kind of change it just for simplicity. But basically, I mean, this would probably just convert into this. Say, I don't know, just say token list or whatever. This will convert into token list equals this, you know, or token, like that. So it would basically just, yeah, I should probably put token in here, make more sense. Anyway, yeah, so I'm not really sure how the syntax is going to work. Again, the implementation normally defines it, because if you say, oh yeah, I want to have like, so what I want to do, right, I want to make this is a mutable pointer, and this is an immutable pointer. That's my syntax right now. And let's try and implement it. And then you find out, oh, that's actually ridiculously hard to actually track. And then it's like, you give up. And then you think, okay, I'm just going to have regular pointers and not, you know, make my life a living hell. It depends how difficult it is to actually, you know, convert. Because it's like, for example, oh, let's just, like in Rust, for example, let's implement the borrow checker. And then you come back 5 years later and you still haven't implemented it because it's ridiculously hard to do that. It's one of those things that sounds simple. Oh, let's just track when variables stop existing, because that's easy. Anyway, so yeah, most of these things are easy. Else is pretty easy to implement. I just haven't done it yet. Switch is actually annoying to do. The reason why switch is really annoying is because everything that's like a case with a number with this, so you have to have like the case with the number with whatever it is, and then you have to have the body, which is a separate node, and then the case is a separate node, and then this is also inside a switch block, which also has a node for the actual thing you're checking for. Because say if you have something like switch, first you have the main node. Inside this node would have a node left, which would be this, whatever's inside this, because this could be bloody anything. It could be, for example, I don't know, core dot thing dot array access 0. So you have to put all that, because it could be this. You could have this linking to this, linking to this, linking to this, or it could be a struct instead of struct instead of struct instead of struct. It could be that. Or it could be something like this dots pointer dereferenced, a dereferenced pointer. So you've got to, you know, you've got to put everything. You could just presume in theory it's just an identifier and then just expect this afterwards, but you'll be limiting your programming language if you did that. Anyway, so this will be a separate node on the left. And then we'd have our own node here for the body, and then inside each body would have a child, and inside those bodies would have the case, which is a separate node, and then have the whatever's in here as a separate node with children, and you are now going insane, and you give up trying to implement switches, and you realize, oh, this is actually pretty hard to implement, right? Yeah, it is. Anyway, that's all for this. I thought I'd give an update. The code is in the description. Because I've implemented so much stuff, it's thousands, it's probably hundreds of lines of code, probably thousands, I have no idea. It's in the description. I'm not going to go through all of it because that would take me probably 30 minutes to go through everything. Yeah, so that's what we'll do from now on. I'll be converting to Go for now, then later converting to LLVM, because to convert to LLVM you need to track variables, you need to track what everything is all the time. Anyway, I'll see you guys next time.